Let's go the other way. Store is going to go from processor to memory. So what happens? We have to give a real set of values. So let's use the same S3, which is our base address. We have an equation that says the effective address, which is where we actually access the data, is base plus offset. In MIPS, we end up with 32 bits eventually for the address and 32 for the data. Actually, they made it. That's what 32 is our most common answer. So in this case, S3 base plus 8 gets us to here. Load or store. Store. Processor out to memory is storing the result. It's like writing on a piece of paper. This is the recording medium. This is the memory. What gets written? Well, load word, store word. Store word, 32 bits. So this cell is going to go here. Next cell is going to go here. We fill up 4 cells, which is the contents of a register. So I've asked you a question, how many memory cells that are 1 byte each is required to store 1 MIPS register? Answer is 4, because MIPS register is 32 bits. Memory is byte addressable. These are the byte addresses. It takes 4. 32 bits needs 4 bytes to store the answer. That's why I gave you this visual. It's actually not in the book. This is because if you can remember this, you can see it, right? So here's an interesting question. We call this word boundaries. Sometimes it matters and sometimes it doesn't. For things like instructions, have to start on a multiple of 4. We call it a word boundary. So between these boxes is a word boundary, is a word boundary. We can't start an instruction here because it's actually getting some bits from this word and some bits from that word. That would be like if I was speaking and you took some letters from the first word and some letters from the second word. That doesn't make sense. Same with the processor. You send it some bits from the first word and some bits from the second word. It doesn't know what you want it to do. What does it do? Blue screen, right? Crash. Why did that happen? Because, well, bad data transfer. We were transferring back and forth. We lost some bits. We actually confused the processor. It doesn't know what to do. It'll just stop before it makes things worse, usually. It's a good strategy. So let's see how this actually works in practice with the statement that you've probably written in C. So we have a variable H, and we have an arrayed variable A. This is the 8th element of A. Now in C, they make it difficult, which actually now it's going to get easier. Their arrays start at 0. Quarter of the time I'll forget, and I start counting at 1 because human beings start counting at 1. That's why Roman numerals are out. Why is that? That's trivia, but it's...
They didn't have zeros?
They didn't have 0. So it was going pretty good for them, you know, MXLIV and all that stuff, and until what? Trade, commerce, accounting. And when you go, if you try to add or large numbers in Roman numerals or try to multiply, good luck. So Arabic had a 0, so that kind of caught on because 0 is useful. Same when we have memory. Sometimes we want to show what happens if all zeros are on the address bus. That's address 0. Same with an array. There's a 0th element of the array. So a lot of times I'll say the 0th element. It's actually the first physical element, but it's numbered 0. If you go to Europe and you get an elevator, they actually have, a lot of places have a 0 floor as a ground. They just start their counting, that's ground. And the first floor is actually the first floor that's built above ground. So that's what we do here. So this is the 0th element, first element, second element. So we want to add to the 8th element, it's somewhere up here. Right? So this is what the programmer wrote. What does the machine actually execute? And this is where it gets interesting. You know, you wrote something, but as we saw in the last class, that may not be what the computer executed. But what matters for energy, what matters for time, is knowing that. So computer science is happy. They go, you know, the functionality, it works, good. But suppose you want to make it work good. You want to make it work fast. You want to make it work efficiently. You need to know what the hardware is actually doing. So in this case, what's the first thing we have to do? I said if it's an array, the data is contained where? processor memory. It's an array. You can't fit an array inside the processor. So that means right off the bat we have to load. So this is like a puzzle. What's this piece? And I know I need to load. Why? Because this is an array. It has to be in memory. This is asking you to add. The add instruction is executed where in the processor? It's in the ALU. Where's the ALU? Is that inside the processor or outside? ALU. Inside. So we have to get the data inside before we can operate on it. T0. So how do we get data into T0? We want to get the A sub 8. So this is the base, S3. Where did that come from? Well, it's given. Okay? You're going to say, well, how did I get that? Good question. It's from the compiler. We're just going to accept it for now. We talk a little bit more about it, but if you really want to be an expert at that, that's another class. So S3 is where the base of this is. What's the base address for this array that's depicted here with these are decimal addresses. What is the base address of this array A? S3. Base address. That's the base address is in S3. That's where the base address is stored, but what is the base address as a number? 0. You have array B in memory. So now I see what base is. That's like the first address where that starts. If you want to see that, go over here. Remember our memory map? So right now we see this start at a different address. We call these fences, actually. Each one of these segments has a certain address range. Inside here we have like this payroll data. Might be like salary from Publix and the salary from I don't know, Best Buy, and then you're adding all these up because you're an accountant and you're not using Roman numerals. And each array that you're working with has its own segment of memory, and it has a starting address. That's the base. You go to the next element, we're going up by 4. Why by 4? Memory's byte addressable. Integer stores 32 bits. It's common, almost every compiler. Anybody ever use the size of command in C? Size of, what does it return? It returns like 4 for an int. That's how many bytes. Now we see it. If you use that before, if you haven't used it, you can continue to not worry about it. So what happens? S3 contains the base address. Even though I didn't give in this problem, if I ask that as like partial credit, you guys are going to say it's definitely 0. If I give you this diagram, right, then you see the base address is 0 because we started 0, then we go 4, 8. This is going up from the base. 0, A0 is where the base is. We're happy because it's not some strange random number. Then what? Where'd this come from? This is the offset. So we add the base to the offset, Y32 to get A8.
It's every 4. So 8 times 4 is 32.
Yes, 8 times 4 is 32. And where'd you get the 8? Well, we're going to try the 8th element. Is the 8th index in the integer array A. Right? From 0, it's 32 bytes, right? So 0, 1, 2, 3, and then 4 is 1. 2 is, so you see the pattern, right? To get to the 8th one, it's going to be 4 times 8 is 32. We've just loaded this into the processor. Have we done any addition yet? No. So we're at the next piece of the puzzle. So add instruction. We know one of the operands has to be what we just loaded.
Storing in 1.
Because?
That's G.
It's G. And what about this guy?
That's H. Storing, that's 2.
So you're saying each element, or and each element of the array stores a 32-bit integer?
That's exactly right, because that's what the A is defined to be integer.
And is that just because it's MIPS, or that's just?
It's just how the C program was defined. Int of A for however big it is.
Okay, and that's why it takes up 4 blocks.
4 bytes.
Well, you're storing now, right?
So we need to add a store word. Store word goes what direction?
From the processor to the memory. Memory to processor.
Store word is storing back from the processor out to the memory. Store word processor memory. So first two is the same, right? No change. It's not a trick question, actually. This is the same. A is an S3, H is an S2. All right, so that gets the data in. It gets it into T0. We did the add. Well, you did add it, but what did the program say to do? It said to add it and do what? Put it into A12. It didn't say put it in any other place, a specific place, A12. To put it in A12, you need to execute this statement. You need a store instruction. You're going to say, all right, I'm getting this pretty good. Can you make it even easier? Anything that's on the left-hand side is a store. Anything that's on the right-hand side that's not in a register is a load. Interesting. Usually the destination is on the... There's exceptions. Not too many, but there are. Store word and store byte are like the most notable exception to that. There's a reason they did this, is the way it's wired up. Remember, these are stored as bits. This register is going to activate a certain part of the circuit, so they don't have to change the wiring. T0 we've added to. This is the result. So we take S2, which is H, right? H plus T0. What's T0? A sub 8. Goes into T0. Then we have to store it back out. Normally it's destination. MIPS is destination, operand 1, operand 2. That's giving you dyadic. Why is it dyadic? Because you have two inputs. Store word. This is actually the source, not destination. This is normally destination. Source. Going where? Whatever is in S3 is the base, plus the offset. Remember, the units are bytes. If they don't tell you anything else, anytime it's memory, memory is always in bytes. If it's in anything else, we have to tell you word or bit. Memory's default unit is byte. It's just like you're driving down the road and it says, speed limit's 55. That makes sense to everybody, but we assume it's miles per hour. You don't want to be square, you just say 55. We say this address is byte address. That's just how they do it. It's implied unless we say word. Question?
If you don't specify the offset, will it default to 0, or do you have to?
Technically, there has to be a 16-bit number here, but we'll see later how that works. If you put it in Mars, I think Mars, if you don't put a value here, allows it to be defaulted to 0. In fact, I know I've coded that before. But that is actually the assembler being nice to you and correcting your mistake and putting a 0 there for you. So yes, it will work.
Okay.
But the machine needs some bits to add to because the adder has two inputs. So remember, in this class, it's not a mystery anymore. So that's a great thing about this course. Even if you're an electrical engineer, it just gets rid of the mystery, right? You type these things and you don't have any idea what's happening. Always think it has to be converted to a voltage. There has to be a voltage on that wire. So the assembler is going to put a 0 there for us. But we know for sure that there's something added there. It's a good question, though. Will the assembler let you do it? They might have error checking and say, hey, it's not valid. Which is 2 slides ahead. We're going to see exactly the case it was on a load instead of a store, right? So load's coming into the processor. Yeah, we'll get to that. So let's see this first. Here's a graphic showing this actually adding. You're going to say, well, why am I going to bother with this? We're going to build a circuit for this pretty soon. For this instruction, it turns out to be not as complicated as we would think, but we said we had an equation, which I just erased, was base plus offset. So here you can see that actually happening. So here is the offset, here's the base, here's the bits of this. This is 24 base 10. Why is that 24 without using your calculator? Because this is 16 plus 8. And this is S3. S3 has a whole bunch of bits, actually. I'm only showing part of it. But to add them, we do what? 0 plus 0 is 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is carry. It's actually 2. The way we write 2 is 1, 0. See? Okay. So how does the hardware actually perform this instruction? We're giving you an insight. We're making you think ahead. We're motivating you to stay in the class to the next module. But this goes into an adder. These are bits coming into an adder. We're going to expand this to multi-bit adder, 32-bit. We're going to give you 3 different designs. Once we have these bits, what's the processor do? So the processor sends an address to memory. What's the memory do? Looks up the data at that address. What does load word do? Computes effective address, sends the address over the address bus to the memory, and wait for the data to come back. Is that it? That's it. Putting everything together here, all 3 so far that we covered. Instruction classes, so we have some arithmetic, we have some branch, and we have some data transfer. Here's the statement of C. It's a good time to make a note to, when you got some downtime, if this is not clear to you what this is doing, you just Google some pages on control flow with C. We don't usually do much more complicated than this, but you should be able to decode what this does. Anybody want to take a stab at it? What this is? What's the statement of C code do? Go ahead. So this is a while construct, and the condition to execute is if the value that's in the ith index of the arrayed variable save, it's actually an integer. Save sub I is just like a sub I, but they just call it save. If the ith element of that array is equal to k, well, what's k? It's a constant. Could be 0, could be 5, could be 100. If those values equal, then we increment I. Well, what did I start as? Well, whatever I start as. If it started at 0, then it becomes 1. If it started at 20, then it's 21. Question, do we enter this loop of code if this condition is not valid? No. In a while, you do not. That's like the only trick, right? They always ask that question. 60 years they've been asking that question in C class, right? So that's like a boundary condition, right? And that's usually where things can break, actually, so they're giving you practice with that. So the question is, what has to occur in the hardware for us to execute this one line of C code? Is there going to be a load? Why or why not?
Yeah, because you have to compare, right? K with the whatever.
Well, K compare is it turns out is an ALU instruction, which I haven't really said that, so I don't expect you to know that. But if we're comparing K to something, that's an arithmetic operation. We're comparing bits, something greater than or less than or equal. But why would there be a load or store occurring in this?
Because it saves in memory.
You got that. Okay, so see, anytime we see an array here, we have to get the value inside the processor in order to compare it. Where does the compare occur? Inside the processor. Where is save I? In the memory. How about what type of instruction we're going to need for this? We need an arithmetic. We're going to probably add will do the job. Maybe add immediate. No, I see that. The difference between add immediate and suppose I was adding plus j. Then you probably won't have add immediate, right? You have to, whatever register contains a value of j. Okay, so let's break this down to steps. What we need to do, we know we need a load word. Load word needs a base and an offset. There's a lot of ways to do it. Here's another way, which is going to show you something kind of cool. What we're doing is these two statements work together to compute the effective address. Effective address with a 0 offset. So actually, by the time we get to T1, this is the destination, right? By the time we get to this instruction executed, we've computed the effective address. We're doing it manually here in a cool way. This is helping us to practice some things, and actually this is what the compiler would produce. And one of the reasons is because this has to be a constant in real life. Now Mars lets you put a register here, so you can keep incrementing either this register or that register to step through an array. In the real hardware, this first term is a constant. We'll explain later why, but it's just the way the data path was designed. In any case, one way to compute the address of memory you want to access to get save I is to do what? Well, this is, I mean, we saw the pattern, right? The 8th element went to 32. 12th element, 48, was where we stored. So how about the ith element is 4. Can we say this is converting from the word to byte? So this is the word address. Why is it word? Because it's an integer. Integer takes a word. You're going to say, I can't remember that. Well, just remember, if it's an integer as a byte, is the other choice, you can only represent 256 different things. We've all had programs that have an int that's larger than, numbers larger than 255. It needs more than 8 bits. It has to be a word. To have a meaningful int, I think they have, you can have char, C-H-A-R. If you do want to use an 8-bit int, you set it, you actually type it, you cast it as a char. That will force it to be 8 bits. But when we say int, it's always 32 bits. So this is an integer array. We have to compute the effective address. So what we're going to do is take I and multiply it by 4. And I'm going to explain why this is multiplying by 4. We have to show you a new instruction. So shift. So we have an instruction called SLL. So what this is doing is shifting. So now back to this. What did this statement do? It shifted. S3, what was S3? I. 2-bit positions to the left multiplies by 4. Suppose I shifted 3 bits, it would multiply S3 by 8. If you want it multiplied by 2, shift 1. You're going to say, I don't need a multiplier to do that? No. If it's a power 2, so we love it. Just like when you took physics, anytime the teacher was cool and made the numbers powers of 10, it's just a shift. Anytime we multiply by a power 2, 2, 4, 8, 16, 5, 12, you don't need any hardware, just shift the bits. So now we multiply this by 4, so you're going to say, okay, well, so why in the world 4? Well, I was a word. We need to load for memory. Memory is always byte addressable, so you had to multiply by 4. Plus what? Well, this is I multiplied by 4 is now inside T1. You're going to say, no, well, that's not I by 4. Yes, it is. These are bits, but bits a digit. If this was just decimal, you wouldn't even think of it, right? This is multiplied by 4. So this started as an address, is I is offset, multiplied by 2 is in T1. We have to add the base to that. It's in S6. Now in T1 is the effective address. Are we ready to load? Yeah. How much offset? 0. Okay. So question, we've got halfway through this machine code. How much of this C statement have we accomplished? Just save sub I. Actually, have we compared it yet? No. So actually up to this point, all we did is we retrieved save I to where? Inside the processor. We loaded it. That's this job, load. Into the processor's register T0, the processor's register space, register file. Then what? Well, there's different ways we can execute this compare. One way to do it is to say, if it's not whatever value we're looking for, in this case K, it's time to quit. Break out of the loop, okay? So this is like an exit condition. If these two are not equal, what are these? Load meant I loaded the data from the memory into the processor. Compare it to S5 was K. So this is save I. Compare with K. If it's not equal, time to quit. Otherwise, time to add, increment, I, go back. So you're going to say, is it a good question? Is this a J? You can put a B and E, but the condition has to always be true. You have to put something that's like 0 does not equal 1 always, right? And we're done with this module. This is showing, again, the abstraction. We looked inside these. We saw bits on the address bus. We saw bits on the data bus. And instructions, we'll talk more about this in the next module. And this is a summary of some of the categories. Sorry for the mess. All right, arithmetic, data transfer, also branch. We covered so far. And we had this construct of registers and memory. They're both storing elements or values, but this is outside the processor. 2 to the 30, why not 2 to the 32? Because each word is